Welcome to Digital Electronics lecture series. This is lecture number 23 and we are starting with how to use IC 7483 as adder and subtractor. Now in the previous lecture we have seen that IC 7483 can be used to add two 4-bit numbers. Now here we will show that this IC can also be used as a subtractor. So this is the diagram here we can see. So here this carry in, which comes from the previous IC maybe. So this is acting as a control pin. So we are adding some hardware. Here we are adding 4 XOR gates. We are not directly connecting input to B0, B1, B2, B3, B4. We are connecting it through XOR gate. And this control one input of every XOR gate is connected to the control pin. Now what is the use of this control pin? We will see that this particular circuit, it can act as an adder as well as a subtractor, and this control pin, it decides whether the circuit will act as a adder or a subtractor. Now when this control pin is 0, then the above circuit it acts as a adder. We can show this. Okay, like suppose if we make this as, suppose this as 0. If I make this as 0, now I want to add suppose 0 0 1 0 with, suppose this is another number 0 1 0 0. Now this is 0, so this 0 goes to each and every input of the XOR gate. This 0. Now XOR output of XOR gate is have an odd number of inputs are high, so this 0 0 will make this as 0. This 0 0 will make this as 0. This 1 0 will make this as 1, and 0 0 is again 0. So here what we observe is whatever input we are giving at this point, we are getting at the input of the IC, and that will be of course simply added. It is acting as a simple adder. Now what happens? So we show that control this pin is 0. It is acting as a adder. Now suppose if you make control pin as 1, now this particular circuit subtracts using 2's complement method. Now what is 2's complement method? Suppose if we want to add subtract a with b, so what we do, we take the 2's complement of b and then we add with the 2's complement, and whatever sum we are getting is actually the result. This I have shown in my previous videos, that how to do subtraction using 2's complement. So we convert this particular subtraction into 2's complement method. So here it works how it works. So here what we see is when control pin is 1, it works as a subtractor. So how it works here, suppose when you make this as 1, when this becomes 1, so a carry in is already given to the circuit, and each and every input of this XOR gate becomes 1 because of this control pin. Now whatever input we give here, suppose we are giving 0 1 0 0, suppose. Okay, so this 0 1 will make this as 1, this is 1, so this becomes 1, 1 1 becomes 0, and 0 1 becomes 1. So what we observe is our actual input is 0 1 0 0, which gets converted to 1 0 1 1 towards the IC. Okay, so this is actually 1's complement. Okay, the input, this 0 1 0 0 is our actual input, and it becomes to 1, it converts to 1's complement because of this XOR gate, and we are adding this 1 also. So actually what we are doing is we are adding 2's complement. This particular circuit is acting as a adder. So because of this XOR gate and this control pin, what we are adding is we are adding 2's complement, and whatever answer we get is actually the subtraction using 2's complement. So this is how we use IC 7483 as a adder as well as a subtractor. Now next we see the designing of a 1-bit magnitude comparator. So this is the truth table. So in 1-bit magnitude comparator, we have two 1-bit numbers as given here, A and B. A and B are the two 1-bit numbers. We want to compare their magnitudes. So because we have two inputs, there are 4 combinations, so we have to compare A with B. So the 3 cases would arise as seen in the output. Either A is greater than B, or we can say A is equal to B, or A is less than B. So we have to check these conditions. So we have to check these conditions in which we have to see whether it is greater than B, is it equal to B, or whether it is less than B. So the first case, A and B both are 0 0. You can see A and B both are 0 0. So this condition gets true, that both are equal, and this condition gets false. So this is 0 0. Now in the next condition, A is 0, B is 1. So A is less than 1. Okay. So this condition becomes true, and these two conditions, they become false. Next is A is greater than B. So this condition becomes true, and the other two conditions, they become false. Now in the last case, A is equal to B, both are 1 1. So this condition becomes true, and these two conditions, they become false. So this is what we get the output. Now in order to design, we need to write the equations here, because the equation there are only 4 entries. We don't need to draw a K-map for this. So let us see what is the equation of, let us take this, suppose this is y1. Suppose this is our y1 output, this is y2, and this is suppose y3. These are the 3 outputs. Now what is the equation for y1? If we see y1, so y1 is this one, this particular table is y1, this particular table, this one is our y1, this entire is y1. So output we are getting at this, this is 1, this one is for A B bar, this is A B bar. So y equal to A B bar. So we require this. Then the second output, this is y2. Now to write the equation for y2, what we observe is, this is the equation, this is the actually truth table. So we get output for this is 1, and this is 1, and the corresponding terms are A bar, B bar, or A B. There are 2 terms. Okay? But this, we know this is actually the output of a X NOR gate. This is output of X NOR gate. Now the last one, y3. So y3, we get output 1 at this here, and this is A bar B. So this is A bar B. So this is the what we have. So we need to draw the circuit, and here is the circuit is here. Okay, here as we can see the y, this is for y3. So y3 is A bar, I will just write it here. Okay, so this is y3, which is equal to A bar B, and this is y2, and this is y1, where we have A B bar. So this is A B input is connected to each and every gate, here through NOT gate and here through NOT, because we require A bar and here require B bar. So this is the final circuit diagram for 1-bit magnitude comparator. Now next we see a 2-bit multiplier. So we have a suppose 2-bit number. Let us assume we have 1 0 and 0 1. We need to suppose multiply this number. How we do this simple multiplication? 0 1s are 0, 1 1s are 1, then we leave a gap, then 0 0s are 0, 1 1s are 1. Now here we see this, I'm circling with yellow. This all are called as partial products. This all are called as partial products, and then we add these partial products such that this 1 comes here, then this 1 plus 0 is 1, this 1 comes here. Maybe if we got to carry, this carry would have also been added this point, okay, from this previous addition. So we have to keep this in mind, that what we have to do is we have to get the partial products and then add those partial products in the next part. So we can generalize this. Okay, this is a 2-bit number. So suppose if we make this 2-bit number like in general A0, A1, and this is suppose B0, B1. These are the 2-bit one numbers. So if we multiply them, okay, so in general what we observe is we get this. Okay, if we multiply them, then this is what we would get is here, as we can see, A0, B0. Okay, this is a partial product multiplication. Then A1 gets multiplied by B0. See this A1, B0. Then in the next step, this B1 into A0, then B1 into A1. This four are the partial products. This one directly comes down. We have to add this two, and we get P1. It might be possible that this P1 this addition may also generate a carry. So this carry will go here, and this will be added, and we have P2. And maybe if there is a carry, that will go into P3. So this final number, this P0, P1, P2 will be our answer. So as observed here, see this P0, the partial product is A0, B0. P1 is B0, A1 adding with B1, A0. Then P2, this P2, what we get is B1, A1 and a carry generated by this particular addition, the carry of P1, and P3 is simple a carry of P2. So here in the first case we require a simple AND gate. Here we require these two AND gates, and we are adding this, so we require adder circuit which adds these two numbers. Then finally we have this B1, A1 is ANDing, and it is added with a carry which is generated by P1. So here we require adders as well as AND gate. So this is how we implement. This is the implementation we can see. So as seen, the first is A0, B0, ANDing of A0, B0. This gives P0. Then we have A1, B0 is AND, so this A1, B0 is ANDed, and B1, A0, and they are actually, we have to add them. So we require a half adder. Okay, this is a half adder. One of the output is P1, and the carry of this, is added with B1, A1. So this is B1, A1. This is a B1, A1. This is added, and the carry generated here. We get this P2, and the carry of this is acting as a P3. So this is the circuit diagram of a 2-bit multiplier circuit. So that's all for this session. Thanks for watching.